Hello, welcome everyone. Am I audible to y'all? Second. Yes, okay, thanks. So if you have any questions, you can type it in the chat. You can unmute yourself and ask me the questions. What I'll do in the 30 minutes that we have for this Q&A is go through exercise 3, where we were training a classical machine learning model. And I'll specifically look at the BBBP dataset, which is a classification type dataset, and look, I'll show you what we need to take care of and things that we need to do before training any model. So let's get started with uh, with that. And if you have any questions, you can stop me in between. If you have any questions on for day one, you can stop me and ask me questions by unmuting yourself or typing it in the chat. So this is exercise 3, and in exercise 3, the task was to use QM9 dataset with Homo as a target value, and this is pretty much similar to what has been done in the videos before. So I'll look at the BBP dataset, which is a classification type 1 and not a regression uh, learning for this. So we'll look at that and we'll see how to download it and transform it. So at first, we would need to download the dataset. And what I'll do for this is just copy the code that we already have in uh, for the previous lessons. So we'll use pandas for this and load the dataset. So we need a URL for the dataset, and that URL would be in the datasets from here. So this link is provided in the exercise on Canvas. So what I would do is, this is the data set that we need. So if you want to get the CSV file, if you just hover over uh, this link over here, you can see that at the bottom of my screen here, you'll see that it's a CSV file. And this is where it's downloaded from. So what I can do is I can just copy the link address from here and then put it in place of this one, the CSV. I would need the other CSV. And you see that once we download it, you can just click run anyway. You'll see that it'll be downloaded and saved into this data frame. And you can see that this has 1, 2, 3, 4 columns with smiles, and P and P is whether it's active or not active, I think, and you have a name for that data set. And if you want to proceed with this, we have to split the data set and featureize the data set, which is what we'll start doing. Before we do anything, we need to look at whether the data set is good or not, right? So let's use RDKit as before and look at whether we have any good, whether there are any bad entries in this data set or not. If there are bad entries, we need to remove the bad entries uh, and then do any classification that we are interested in doing. So first we'll install RDKit here, and then what we can do is we can do the featureization of this. Before doing featureization, let's look at the data set itself and analyze the code for it. And we could do that as we did in the initial lesson of dataset, where we use the uh, mole from smiles and all of that. But there's a good code called pandas data structures, and That's in RDKit. It's called pandas tools. And if you say from rdkit.chem, I think import. So we'll use pandas tools, and I'll show you what benefit we have of panda tools over the other ones. And the the way we do it for pandas tools is you say pandas tools. That's where it pops up. So if you have any questions, you can unmute yourself and ask me questions. And so this is, let's see whether I can get the link for that. So pandas tools is an easier way to look at all the molecules at once. And let me just pick it up from exercise 1, where we have this. So this is the pandas tools. And what this helps with is converting the entire data set into 2D objects, 2D things. And so what you can do is we can use pandas data tools and pass in the data frame and what we want the data set to be called. So let's use this. So pandas tools and data frame, and we need to tell where smiles are, and it's in the smiles column. And what we want the molecule to be called, let's call it molecule, and say pandas tools, and then run this. This is going to convert all the smiles to molecules. Instead of using the code that we had before, you can just use this code, and then this code should give us a nice data frame now. So if you look at the data frame again, you'll see a column with molecules in it. And over here, you can see we have molecular structures for those entries. And sometimes the errors usually pop up at this level where the smiles itself are bad. So we cannot create molecule objects. So your featureization will fail at this point. And that's a good point, a good way to find out whether everything was good or not. So if you look at this data set, we should have 2000 some entries, uh, yeah, 2050 entries in this data set. But let's see whether all entries are there or some data is missing in this data set. So what if I do mol? So df.mol will give me all the molecule objects. And if I say if something is missing, it's not available, or is NA, is a command which tells us whether something is missing or not. So it will give us a value that's true or false, true or false. And what we can do with this is just filter the data with something like this. And then it now will get the data set where all the entries are missing. So we see we have these things where smiles look something bad, like a slash is problematic, I think. And that's why we don't have a molecule object. So if we had a molecule object, it would show a 2D representation of it, but it failed to do that in these cases here. So we need to remove these entries from here, right? So what we can do is this code over here gets us entries which are true for these values, which molecule doesn't exist. If you want to negate it, we use this sign, and this would give us all the data set where we have something like this. So we don't want these entries, so we'll just remove those entries. If we do that, we'll see how many entries we have right now. So earlier we had 2050, and now we have 2039. So it means that the molecules were bad, and that's not good to proceed with. So we first need to remove those entries. And if you all encountered this error where you try to featureize it, it's because of this, because the data set is not clean enough. And that's something that you need to do before doing all of it. And I see a question which is telling that there was an error when I was trying to get molecular weight of the compound, and this is the reason why it happens. When you do molecular weight, you don't have a molecule itself, and our kit is not able to generate a molecule, and that's why it will give you an error while doing this. So here we see that now the data set is clean. So we need to save this data set. So I'll just call it a clean data set or something. And I'll set it as clean data set is this. So it will remove all the is where molecules were not generated, and you have a clean data set. And we can proceed further with this clean data set now. So first thing to do is featureize it or split it. And I think that if you featureize it first and then split it, you avoid some a repetitive task of doing it for the training, validation, or the testing data set. So there's another question. So will it remove all null values from all columns? So right here, this code will only remove null values from the mole column. And if you want to check the other columns as well, you can do it. There are multiple ways of cleaning stuff. One, if you want to remove everything from all columns, so if you use drop NA, this will remove everything from all the columns, all null values from all columns. But is that what we really want to do over here? Maybe not. We just need to look at molecules, and we could also look at, let's say, the target values itself, which is P and P. So if we look at these values, first I would look at the values itself and see how many values we have. So we have 2050 values, and if I say is NA and put a thing on top of it, and let's see whether it gives something. So it does not give anything that is null value in this column. But we did see that if we put in mole over there, we get a bunch of null values. So this means that there's no null value for the target. And in that case, I don't need to uh, I don't need to do it for other columns, but you can do it for all columns if you want, and it will drop only only the rows where we have null values. So the other follow-up question is, by removing a null value from a column, does it drop the entire row or entire row with null value? Yes, it does. So when we dropped this thing, when we looked at the molecule data set and we say uh, drop NA, so it will drop everything. So if I can do something like this, mol dot, there's another one, drop NA. So even if I do this, this should give me the same result as clean sheet. And here we see we have 2039 values again, and not the 2050 that we started with. So you can even use this drop NA to drop null values in it, or you can use this way. So there are multiple ways you can reach to the same conclusion. Okay, I hope that helps. So you can use drop NA, or you can use something like this, and it'll remove all the entries with null values. So coming to featureization, so let's start featureizing it. And the reason we need to do it is because we have the smiles representation, which was here with strings, and we need some sort of ones or zeros or some numerical representation of this molecule. So we need to put in uh, a transform that does that. And for this case, we can use any transform. We have the splitting, which is based on scaffold, which is based on molecular weight. Sorry. So we can use any of those splitting, but let's featureize it with something. And for this case, I'll use the uh, let me install DeepChem first over here. So if I want to featureize it, let's install DeepChem, and I'll be using the Morgan fingerprints or circular fingerprints for doing this. And uh, I think there's a question regarding featureization too, which is molecular representation sensitive to stereoisomers? So the molecular representation that you generate in RDKit is stereos isomer sensitive. You can say whether this is what type of isomer it is. There's chirality in those molecules embedded, and those can be converted to uh, the features that you generate. So you could have a vector in the vector. You could have one placeholder which says whether this is which type of stereoisomer that is. But yes, stereo, it depends on what representations you are using. And even sometimes circular fingerprints, if you look at the lesson that we had on molecular representation, we had some stereoisomers, like whether there was a dash or a wedge type of thing. And the placeholders for ones and zeros in a fingerprint vector is also dependent on whether it's a dash or a wedge. And we can account for that always, stereoisomers. So over here, let me use use the RDKit featureization. Let's featureize it. We have import this, and then we use features of yeah, we use the featureizer from DeepChem, which is circular fingerprint, and we'll run this. So if you're using circular fingerprint, remember it depends on the molecule size. If the molecule is small enough, your feature of 100 is good enough for representing uniqueness in the molecule. But if you have a large molecule, let's say it's having 100 atoms, and in that case, there'll be some collusion of ones and zeros where you put in. So there may not be specific places where there should be an alcohol group of primary alcohol, a secondary alcohol, or tertiary alcohol. With alcohol group is an OH group, and that requires increasing the size. So if you have a large maybe like 1,000 or uh, 2,000 or 3,000 size, you'll have enough space for the large molecules, and you'll have uniqueness in the vector. But if you use a smaller one, you may lose something in that. But it also brings up another uh, limitation, that if you have a small molecule, then a large vector would have just zeros everywhere, and your model would not be trained so good if you have something like that. Okay. So it's a trade-off between how big you want and how clean you want it to be. So let's apply that to our clean data set. Did I call it clean data set? Yeah, clean data set. So I'll use this clean data set and featureizer. Okay, I do need smiles, and then let's do the featureization for this. So I'll use the fingerprint featureizer, which I created on top. And once this is created, it's always a good idea when you do something to look at it always and see whether it's generated or not. And it's ones and zeros. And there's one thing that we need to note. I've stressed on this in the lesson 2. If you see, there are these two brackets in here, so that means this is an array, an embedded array, and that creates problems sometimes when you're looking at generating it, keeping this as an input for anything. So we need to convert this into a list. So you'll see the difference over here when I apply that, and I'll show you what it looks like. Let me pull out that code somewhere. Where is that? That's here. So let's see what happens when we do something like this. So this is a code where you use clean data set, clean data set. So we this is like a function. You want to write a function, but you don't actually want to write a function. So what you do is for each value of x, so each x over here would mean an entry in this data set, fp. For each fp, we take the first element, and because this is a list in a list, if you think of something like that, the first element would be just this thing on the inside, and that's what we want to do, and then convert it into a list. And if we do something like that and then look at the clean data set and fingerprints, you'll see that the extra over here, the extra bracket is removed, and the extra removal of extra bracket converts it into a list, and that's what we need as an input feature. So the question is the Lambda function. So Lambda function is used when you don't actually want to write a function to do something, and you want to apply it repeatedly. This is like a for loop, but you're not writing a for loop kind of thing. So what this does, a Lambda function. So this is the standard syntax for this. So you'll have apply and Lambda. So it says, okay, so you need to apply some function to this column, and that's what we even did before. If you look at it, which is here, so we had the smiles and we applied the featureizer.featureize function to smiles. Now featureizer.featureize function is a well-defined function. So you have def definition followed by the name of the function and what that function needs to do. But can we see that? Maybe. So yeah, so if you look at this function, so it feature-wise data points, log entry, and all of that. So it does have a function format. But over here, this is a small thing that I want to do, which is I need to take the first value of this entire array and convert it into a list. I can write a function to do that, but it's not necessary to do it. It's just small code. So what I do is I use this Lambda function. So it says Lambda x, and in front of that, you need to say what that function is going to do. And for each x that it gets, it's going to take the first value and return a list. That's what the entire thing is. And it's if I want to add a complete code for it, it'll be like make list and then pass some x values, and these x values would be the fingerprints. And then what I want to return is return list of x0. So essentially writing something like this, we can just write it like that, where we just look at what we need to do with the input values that we get from x. So x will be the fp, and we do something like that. I hope this helps. And once where were we? Okay, so we created the list, and once we have the list, I hope I didn't run it again. Let's see. Okay, so once we have the list, we can split the data set and train it. I'll not look into splitting of the data set because it's you just put in the data set and use the splitter. So you can look at different splitters into it. And if you have any questions regarding splitters, do let me know here. I'll address them, but I'll just skip the splitting part and just get a fraction of a training data set. So train data, I'll randomly take a fraction of it. So clean data set. So clean data set, I'll take a small fraction. Sample fraction is equal to 0.8. So let me take a 80% chunk of this and call it a trained data set. Okay. And we can even use the more elaborate ways of splitting it, but let me just do this. So now, yeah, so what we need to do over here is whether predict it's 1 or 0, whether it's active or inactive, right? So this is a little bit different from uh, the regression example, where we try to predict a continuous value. So what we need to do is use a model that does that. So SVC, a support vector classification, is one type of model. You can do other types of things. So there are classifiers for regression models too, but we are using a support vector type of classification. And if you remember support vector, what it does is you have your data set, you have your inputs. Those are the x's, or in this case, we have the fingerprints over here as the input. What it's trying to do is, given these 100 dimensional inputs, it is trying to find a higher dimensional one, which is 101 dimension. And in the 101th dimension, it's trying to segregate those two things, which are active or inactive. So, and it's trying to use some sort of a transformation to do all of this stuff. So there's something called a kernel, which transforms these inputs and then tries to form a hyperplane so that you can have active on one side, inactive on the other side. So all of these things are in the scikit-learn page, and I have provided the links for scikit-learn. And over here, I'll use the classification model and classification. And let's import this. Or it was SVC. I forgot what the model was, but let's see. SVC. Okay, SVM. Okay, so we need to look at, okay, so if you see, you may be asking, okay, how do we choose the model and how do we write the model? Okay, so if you look at any of the documentation, you will see that, okay, this is the SVC model that I want to use. Okay, and if I want to use this model, you'll find some code below as to how to use it in the example over here, as to how something would be used. Like, so you have from sklearn.svm import something. But what you can do is, even by looking at this top thing, so the first part would be the import part. It'll be from this, import this function. And that's what you're going to do for most of the part if you're not too familiar with Python. So just say from sklearn.svm. So from svm is what I need, import svc. So if I do that, we'll get that part. And we can follow the things here same way. So first you can create a model and other things, but in interest of time, let me just use the old code that we have for this. The first would be create a svc model class, so svc, and then you'd have your model is equal to svc.fit. So this is all you need to do, and put in the values for this. So in our case, it is train data set. We need to put in the FP as the values, and all of these need some specific format, and it needs to be a list of all the values, and that's why we need to do this thing over here. And these are the X values. Now we need the Y values. So you can just copy this, and let me use the Y values as P and P. Oops. P and P, and then run this. So the model is trained. You can see the models over here trained pretty quickly, but if you look at more artificial neural network, graph neural networks, it takes a lot of time, as those models need a lot of parameters to do it. And you can look at the score of this model.score, and for scoring, you need to still put in some data set, I'll still use the data set, the same data set, and see how good the model does on prediction on the test data set itself. So these are the X values and these are the Y values. And let's see the score. And it's 0.93 of R squared. So this tells you how, if the R square value is close to 1, it tells you, okay, this is great, because the correlation between the predicted values and predicted values using this value, the X, and the true values, which are the ones in the data set, is exact. But if it's slightly off, it's okay. And 0.93 is a good result to be at. And with this, uh, we are close to the end of this Q&A session. So if you have any questions, do let me know. I can discuss those questions too. Do you have any questions for me? And this recording will be made available again, and we can you can go over it again. So there's another question, which is how to improve the value of how to improve the values other than kernel change. Okay, so the question is, oops, let's see. Um, so if you look at this function, there is a kernel, and let's see whether it loads up. Yeah, so kernel is one of the parameters that you can change here. So this kernel is one parameter, there's degree, there's scale, there's tolerance, and other things that you can change. And the question was, in the lessons that we looked at using support vector regression, we just changed the kernel and saw how good the predictions were. So there are other things that you can do is with the data itself. So one is the model. You can change the model, and the things that you can change are over here are pretty much limited. And you have the parameters, regularization parameter, and other things. You can even look at how to changing this regularization parameter if you want. And yeah, the scales 1 by n. So you can change these values, any of these values, and these would change the model itself. Sometimes the data needs to be changed, and if you want the data to be changed, then we need to look at the featureization itself. Can we improve the features, and are there other ways to add more features to it? Maybe you have a fingerprint over here and fingerprint is not good enough, or you can change the fingerprint size. So the size over here initially we took as 100, I think. Let's see, what was it? Yeah, the size was 100, so you can increase the length of this of that, and maybe increase the radius. So radius tells you how many bonds you're looking at. So they are looking at 2 bonds away, you can make it 3 bonds away, 4 bonds away. With that, what happens is the featureizer becomes larger and larger, and hopefully that would improve the predictions. But sometimes it's just the limitation that no matter how much you give the inputs, how big a input you give, and the model is just restricting it and not able to learn a lot. But what we have looked at, the SVM models are pretty good, and they reach somewhat good accuracy as some machine learning or artificial neural network models. But sometimes you're just limited, you need to use something else like the deep learning methods to get more accuracy. So there's another question. If I have a reaction data set, does it make sense to concatenate the feature space of both reactants and fit the model? Correct me if I'm wrong, but I assume in classical methods, it does not make sense, but with NN, it does. You can try. There's no harm in trying with these methods. What There's regression methods. These regression methods are pretty good, and they do. If you look at kernel-based methods, so kernel is a way you transform the input, and that's what these methods over here use. So you have the kernel over here set to radial bias function, so you can change those kernels and uh, uh, get somewhat accuracy little bit close to NN, but you can definitely do that and put in the values of what I would do in this case is fix the reactant values. Maybe you have a featureizer, a fixed featureizer for reactant A, fixed featureizer for reactant B, and then put in those values in here. And as you said, you can concatenate them and try doing it. And this would be something worth trying. And I would say the ridge regression, the kernel ridge regression model and SVM models should be pretty much decent in prediction. But again, those are not sometimes as good as the graph neural networks or something that you look at in the in the later part of this course. But definitely worth trying, and concatenating is one way to do it. There's another question: which platform would be better if you want to perform some ML models? Is Colab good enough? Uh, there'll be a session on the last day where I'll discuss about doing ML on Colab too. So what we are doing right now is using the CPU. If you look at this part over here, the top part, we are using backend, Python, all of this. But right now, this is CPU based. And if you want to use GPU, we can even use GPU on Google Colab. And it's pretty decent to run small models, which take like an hour or so. But some of the models that uh, we train for like research level things are pretty large, and you would need a high performance computing to do that with GPUs. If you train the models on CPUs, as you will see in the later examples that we do on graph neural networks, it takes about 5 minutes to do just one epoch and one round of training. But I'll show that how on GPU it could be done much quicker, and on the same Google Colab notebooks. But Google Colabs are good for small projects if you don't have access to machine learning. So there's a follow-up question regarding the reactants. So is there a way to incorporate information that two feature space belong to two different reactants and propagate across the reaction graph? So over here, what is happening is uh, these models over here, you're giving them ones and zeros or some features of it, and there's no graph kind of thing that's happening here. So what I would think of is you have your reactant 1, reactant 2. I would make sure that all the reactions have this reactant 1 and reactant 2 giving you product, and whether or not it's giving you product. So reactant 1, reactant 2, and it's like classification works or not works, something like that. So in that case, you have a fixed featureizer for reactant A, fixed featureizer for reactant B, and concatenated together would be your input for the model. And you make sure that every time you input it, the reactant A should be the first one, the reactant B should be the second one. If you mess it up, the model is going to predict something else. But as long as you make sure that the input is consistent throughout, it should work pretty good. And you can just concatenate features and then pass it uh, to the network. And or whether it's uh, a simple classical machine learning model like this or more complicated neural networks, you still need to make sure that the first thing is reactant A always, the second thing that goes into the featureizer is reactant B always. And you can't change and say that it's okay, this is what it was, or something like that. As long as you are consistent with your input, it should be okay. I hope that helps. So if you have more questions, you can always let's see. Yeah. So if you have more questions, you can always go to the discussions and then put in the questions in here. So if you have any discussions, oh, there were some discussions. Okay. So you can put in things in here. I forgot I should look at these discussions. Sorry, but I'll look at them today, and I'll I'll let if there are any questions, I'll answer them. But do put them in the discussions, uh, and we'll have another session tomorrow. And thank you everyone who showed up, and I hope to see you soon tomorrow. Till then, have a good day, a good night. See ya.